Okay, let's look at example 9.6 in the book. We have a triangle, a right triangle, and we're supposed to determine the product of inertia with respect to this. So we have, with respect to this axis right here, what is the product of inertia of this whole thing? And then later we're going to turn around. Part B says with respect to this centroidal axis, what is the product of inertia? So first off, product of inertia. What is product of inertia? So I xy is integral xy dA, right? So let's draw a little differential strip. So there's our differential strip. Well, what do we know about that differential strip? That dA is defined as, it's just a rectangle, right? So the area of that rectangle is the height times the thickness. The height is going to be y, and the thickness is dx. Okay, can we use that here? The short answer is no, we cannot. The reason being is we are holding, with this differential strip, we hold x constant. Anywhere along this differential strip, x is the same value, but y is not. And when we're doing this thing with the x and y here, we have to be able to hold we simply can't draw a strip like this. We can't get away with this because it's the reason we can go from doing a double integration to a single integration is that we're holding one thing constant the whole time. So what do we do in that case? Well, what we do is we say, hey, I know something about a rectangle that looks like this. What do I know about that rectangle? If I look at just that dixy, I know what that is. I'm going to say that's dixy bar plus xy times dA, right? It's using the parallel axis theorem saying relative to this point right here, hopefully I'm making that nice and clear, that the product of inertia of a little rectangle is the product of the inertia through the centroid of that rectangle plus the distance that it goes in this direction and the distance it goes in this direction times the area of the rectangle. Okay, but what do we know about this? This is a rectangle. It's a symmetric rectangle, so that goes to 0. So really dixy is simply the distance from here to here, which is, we're going to call it x bar of this little element, and then the distance from here up to there, which we're going to call y bar, that little element, times the dA, the area of the little element. And that's how we're going to do it, because then we can go through and we can integrate that, right? Integrate that, and in this case we want to go from 0 to b of that. But let's define some things. X bar, this differential element, what is it? At any point in time, it is going to be x, right? If the differential element's over here, if it moves over here, it's going to be x. Now y bar, this differential element, is always going to be halfway up, because again, it's just a triangle. Remember, it's just a rectangle. It's just a simple rectangle, and the y bar is always going to be in the middle, which is going to be 1/2 y. And what is dA? Well, we defined it earlier. It is y dx. So therefore, dixy is x times 1/2 y times dA, which is y dx. And so if we want to integrate that, we can figure out what, so ixy is integral from 0 to b of 1/2 x y squared dx. So the thing here is we need to put x and y in terms of the same thing. Well, this line, this line right here, we can figure out the math on this. This is y is equal to h times 1 minus x over b. So you can simply swap that out for there. And so ixy is integral from 0 to b of 1/2 x times, I'm going to pull the h squared out because it makes it easier, of 1 minus x over b quantity squared dx. You go through and you do your math, 0 to b, so we'll pull out the b squared over 2, and you're going to have x times 1 minus 2x over b plus x squared over b squared, all this times dx. And you end up getting that ixy is equal to, once you integrate it and then substitute in b's for the x's, you end up getting 1/24 h squared b squared. Where did my h go? I converted this to, sorry, this is an h, that's not a b. This is an h, and I couldn't read my own writing. Sorry about that. So you end up getting 1/24 h squared b squared. So that is the product of inertia. That's your answer for part A. That is a product of inertia relative to the x, y coordinates as shown there. Okay, now part B. What are we supposed to do in part B? We're supposed to determine relative to the centroidal axes that are parallel to the x and y axis. So those, in other words, this axis right here. Well, what is the beauty of the centroidal axis? That is what the parallel axis theorem is using. And so we can use the parallel axis theorem for that. So what do we know about the parallel axis theorem? We can say IXY is XY bar plus XYA, right? And so what do we know here? Well, we know this. It is 1/24 h squared b squared, right? We don't know this. This is what we're looking for, IXY bar. It's this, the IXY at the centroid. But we do know how far it went in x and y. How far did it go? In x, it went 1/3 b. To get from here to the centroid here is 1/3 b. In y, it went 1/3 h, right? To go from here to here is 1/3 h. And the area is 1/2 bh. So therefore, I'm going to swap sides of these, right? And I'm going to say IXY bar is 1/24 h squared b squared minus 1/9 times 2, 1/18 h squared b squared. So IXY bar ends up being minus 1/72 h squared b squared. You'll notice it is negative, and that's okay because the nature of this equation right here, you can have negative answers as your products of inertia. So the product of inertia of through the axis that passes through the centroid is negative 1/72 h squared b squared. So what if it asked for some other random place? So here, I'm going to redraw this triangle just to make it a little clearer. So right now we did this product relative to these axes, right? We did it relative to the centroidal axes. What if it wanted to say over here? Well, quite frankly, that'd be really difficult. What is unique about this spot right there is that you can go through and use the parallel axis theorem. That's the only place where you can use a parallel axis theorem. The nice thing about this axis right here is it's pretty easy to define x and y relative to each other. If you go to the other spots, you can do it, but it's just going to take more work.